Okay, good morning, welcome back. Happy Wednesday. Here we go, middle table right here. Thank you. Yes. Today Monday schedule? I believe so. My Mondays and Wednesdays are the same, so I ignore. Yeah. Okay, so today is the 17th. We are covering more on substitutions. A couple of things happening right now. Project number 2 is due. Go ahead and throw it in the green folder if you have it done. Project number 3 is assigned. Go ahead and grab one from your table right now. 2 people asked me before class if they can hand the project in a little bit late. I grudgingly said okay, so I'm going to extend that to anybody who feels like they could benefit from a little bit more time on this project. So officially the new due date is 3 p.m. today, right? 3 p.m. today if it comes in under my office door. Yeah, so 3 p.m. As long as it's handed in by then, it's on time. After that, the penalties start to accrue, all right? Okay, so I think that is good. Yeah. All right, and next class I will hand out a quiz that will be due next week. Any questions on the calendar? Quiz number 3, coming up. Okay, so here we are on page 67, and we'll start up here at the top. Here we go. In this class, we see how to use the substitution technique on definite integrals. All the ones we did last class were indefinite integrals. We'll also see some weird or tricky substitutions. So in the demo, there are 2 ways to evaluate a definite integral by use substitution. We're going to try both on this particular integral right here, integral from 0 to 2 of x times x squared plus 1 cubed. The only thing that's different about this from last class is it's a definite integral with limits on the integral sign. So there's an incorrect method. Don't worry too much about copying this part down because it's not going to be right, but let's give it a shot. First, we will try our u substitution. By the way, there is a way to do this without any u substitutions at all. If you imagine taking x squared plus 1 cubed and expanding it, yes? Just multiplying it all out with lots of distribution. You'll get some big polynomial. Then you have an x in the front, which you could distribute, and you'll just get a polynomial, and integrating polynomials is easy. So you could do this without any u substitutions, but if we changed it from a cube to a 35th power, then all of a sudden that expanding becomes a lot more onerous. So let's practice with the u substitution method anyway. So good choice for you oftentimes is the thing in the parentheses. Let's give it a shot. We'll take our derivative, du dx in this case is 2x. We'll solve this equation for dx. Let's see, so the du here, we divide by 2x, multiply by dx. Can we get that? Is that all right? I suppose you could copy that down if you wanted to, because that part is all okay, and it's going to be part of the correct way of doing this too. And then we start to substitute. This guy equals integral 0 to 2. We get the u in there in the minimal way, which means what? So it's u cubed, right? And so we can't have the u without the cube. They're attached. The dx becomes du over 2x. So far, so good. And then we copy anything else that hasn't been replaced yet, which is just the x in the front. Good. And then we cross off the x's, we cross our fingers and make sure that all the x's disappear, which they do in this case. So I'll just rewrite it 0 to 2, u cubed to u. And that's great because that's an easy antiderivative, right? Add 1 to the power, divide by the power. What's that? Oh, the du wasn't done. Let's see, du over 2. Thank you. So there's a 1/2 in the front. Okay, so far so good. And then we're going to change that u. U is going to go back to an x squared plus 1. So it's x squared plus 1 to the 4. Let's mush together the denominators and get an 8. And then we'll go between 0 and 2. and then we're just going to plug in. So let's see, 2 squared is 4, plus 1 is 5. 5 to the 4 is 625. So 625 over 8. Minus. It's really tempting when you see a 0 on one of those limits to just assume that you're going to get a 0 when you plug in. And oftentimes that's correct. Do we get 0 when we plug in 0 for x? We don't. So just make sure you actually pause and see if you really do get 0. You plug 0 in, you get 1 to the 4th over 8. So 1/8 there. So 624 over 8. And how much can we reduce that? How much is it? 78. Wonderful. Okay, so 78 is the correct answer. We did lots of good math, we did good calculations, but we're not going to get full credit for this because there is a blatant lie that we've written on the board here. Suppose that you ignore lots of what's up here and we're just going to focus our attention on this stage right here. A little bigger. There we go. Okay, if you saw that and nothing else, what would you do next? You see this in front of you. What's the calculation?
Just plug in 0 for u.
That's what we do, right? That's what this says to do, is you plug in 0 and 2 for u. Is that correct? It's not. It's 0 and 2 for x, and u has encoded in it some invisible x's at the moment, right? So that's the problem. It's not that we did anything wrong mathematically, like our logic was sound. But that right there is a lie. It's just not accurate. We fixed it in the very next step when we changed the u back to x squared plus 1. It's good in the next step. That's correct. But this lie in the middle is a problem. So how do you avoid lying? Let's see. We are going to change just a tiny bit of the process that we wrote up above. I'm going to grab this guy right here. Okay, so this thing became integral. There was an x there. The x squared plus 1 became a u to the 3rd. And then this guy was a du over 2, du over 2x. And then we crossed off the x's. And at that one moment right there, the only variable is u. Yes? This is a u integral. And so having a 0 and a 2 as the limits here are just not right. All we need to do is change them to the right values of u. So I'll remind us that the very first thing we wrote here was u equals x squared plus 1. So all we need to do is change the x's to 0 and 2. Those are the original x limits. If x is 2, how much is u? 2 squared plus 1 is 5. If x is 0, how much is u? 1. And so the correct limits on this u integral, 1 and 5. And then we do our antiderivative. So u to the 4th over 4. There's a 1/2 still in the front. From where to where? From 1 to 5. But now that the 1 and the 5 are not lying to us, what step do we avoid from the previous method? We just plug in for u right now, as opposed to going back to the x's, right? There's no need to go back to x squared plus 1. We've taken care of that. So now we just plug in for u. So we get 5 to the 4th over 8 minus 1 to the 4th over 8, which is the same calculation that we did up above. So doing things the correct way, which is this bottom way, is just a trade-off. You're doing extra work here when you change the x's into u's, and you're doing less work here because you don't need to go back from the u's to the x's. Honestly, I think it's the same amount of work either way. So why don't we just do it the right way, given that it's the same amount of work either way. Trevor. If you do a u substitution on any definite integral, it is incorrect to use the first method, because at some point in the middle of the process, while you're still writing u's, you have values of x. And so like anytime you do a u substitution with a definite integral, let's do it the bottom way, where we change those limits. Other questions? It is. Yeah, this is not true, because if you just looked at that, you would plug in 0 and 2 for u. That's what it says to do. Right. So as soon as, I think it's just written down here, if you actually do the u substitution, you really need to change the limits of integration at the moment the variable changes from x to u. And that's what we did the second time. Still inside of the integral. As soon as we changed from x's to u, we got to change those limits. Okay, when we're ready, moving on to the next page. This is the integral of tangent of x dx on that quiz number 2, where you just memorized a lot of derivative and antiderivative rules. They all should have looked familiar to you except for this one, which I said at the time, just memorize it's ln of cosine of x plus c. So let's fill in that gap for the thing that I asked you to memorize. So tangent is really what over what? Sine over cosine. Which appears to make the integral worse. It looks more complicated to me now, but if you have an integral with a fraction in it, you might always try a u substitution. Which piece am I recommending for the u, top or bottom? Is the bottom. If you have a fraction and you're going to do a u substitution, try the bottom. So let's try it. U equals cosine of x. Derivative of cosine is negative sine. And then at this point, we automatically solve for dx. So this is kind of, for me, it's not a cross multiply, it's a divide by negative sine and multiply by dx. So du over negative sine equals dx. So if you have a fraction, u substitution often works. Yeah, it's just a general rule. It's on the reference sheet for u substitution, but you'll see why letting u equal the bottom is a good choice in this case in just a second. Okay, so here we go. This equals integral, got a fraction. Just trying to get my u in here. Where is it? It's on the bottom. I'm not copying the sine of x at the moment. I'm just putting the u minimally. And then we're changing the dx. What is the dx equal to? Du over negative sine x. And now we copy whatever is left over, whatever hasn't come over yet, and that's the sine of x that's on the top. And then we hope that anything with x in it disappears. Does it in this case? It does, right? Sine of x, just left with a -1 down at the bottom. So this integral becomes du over u, -1 at the bottom. I'm going to pull outside. That's just a negative in the front of the integral. So negative integral du over u.
What is the negative integral of 1 over u?
Same thing. Yeah. Yeah, and this is ln, isn't it? Or are we used to writing it more as a 1 over u? I think you might be right, Coleman. Is this the more familiar version of that? Yeah, 1 over u du. And hopefully we recognize that's ln of u, yeah? Okay, so Ben, this is why we let u equal the bottom, in the hopes that it's going to become an ln, in the hopes that it's going to be a 1 over u du. If you tried letting u equal the top, you'd have this cosine of x in the bottom, and if you end up with like a u over something, like that's not as, we have a rule for 1 over u. We don't have a rule for u over general stuff. Yeah. Okay, so this equals, copy the negative, this becomes ln of u plus a constant. There was that technicality about the absolute value, so we'll keep putting it. And then finally, negative ln of, change the u back to cosine of x. Good question. Do we need to put the absolute value or are we going to lose points? So yeah, I'm going to answer that question in just a moment. Any questions on this? Aside from why the absolute value mysteriously appears when we do this ln. It's a negative ln of cosine. Makes sense. It's just a u substitution. Okay, in number 4, it says, let's take a detour to figure out why the absolute value comes in. And this is something I've been like teasing for the last few classes. I'm actually going to skip it right now. It's really just a technicality. It's not interesting. And I'd rather we spend the extra 5 minutes practicing u substitutions today than this technicality. If you are interested in why this absolute value mysteriously appears, just see me right after class. It'll take less than 5 minutes to talk about. I just don't want us to do it during class time. Just don't think it's worth anything. To answer Costanza's question, I have no plans to take points off if you don't put the absolute value. But if you don't put a plus C, that's where my red pen comes out. All right, number 5. Sometimes it's not easy to make the u substitution work because we have original variables, x's, lying around and need to get them in terms of u. I have always been bad at recognizing this kind of weird u substitution. Let's give it a shot here. X squared times the square root of x minus 1. Okay, so we'll try u substitution. If you see a radical, standard thing to try is the thing inside without the radical, just the stuff inside. In this case, du equals 1, so du dx equals 1. And so therefore du equals dx. Okay, so we get our u in here as simply as possible. So how can I get the u in there with the fewest symbols? Square root of u, right? It's inside of a square root. Can't do anything about that. We change the dx in this case to what? Du. And then we copy whatever hasn't come over. X squared. And then we cross our fingers and we hope that all the x's cancel. And in this case, they don't. And last class, I would have said, okay, it didn't work. We need another technique. But in this class, turns out there is one other thing we can try. And if this other thing doesn't work, then we need a new technique. But one other thing we can try. And that's to say, well, you know, I'm really hoping that this integral has only u's in it, no x's. There's an x squared there. If somehow I could replace that x squared with some u's, legally replace it with some u's, then maybe I've got a chance. This very first equation we wrote in blue is a relationship between x and u. And I can solve that equation for x and then change the x squared into something with u's in it. And then just see what happens. So let's give it a shot. Solve this equation for x. Add 1 to both sides. And therefore x squared, which is the thing that we want, is really u plus 1 squared. So this equals changing the x to a u plus 1, still squared, square root of u du. I'm not saying it's going to work. I'm not saying that's any better, but I am saying it's something with only u's and no x's, so at least there's a chance. Everybody buy that it's equal to the original? Okay, what's that? You buy it. All right, so let's see what we can do here. I guess we could distribute that u plus 1 squared, expanded. So that becomes a u squared plus 2u plus 1. And typically when we have radicals, we change them to powers. So u to the half. And I could distribute. So let's give that a try. Okay, so u squared times u to the half. Keep the base, add the powers. So 2 plus a half. Yeah, 2.5, right? 5 halves. Plus 2u to the 3 halves, 1.5, plus u to the half, du. And what do you think of that integral? Can we do it term by term? We can. So this is going to work. I call these guys the weird u substitutions because you do the u substitution, you still have x's left over, which is normally the end of the game, but sometimes, just sometimes, you can finagle it. You can change those x's into some other stuff with u's in it and get something that you can deal with. So how do you know when to stop and when you can do it? I suppose you try to do it every time. Like you hope that the x's disappear, and if they don't, you just change the x's into whatever you get for u's. There's a good chance that the thing that results, this guy in this case, isn't something that we can handle. But if it happens that maybe we can do some algebra and get it to a place where we can deal with it term for term, then it worked. Yeah? Different u substitution, or we'll have some other techniques coming up. Yeah. But if, for example, this guy right here at the end of the day turned into something like u squared sine of u du, like let's say that's what it became after we did this funky changing the x's into u's, I look at that and I say, well, I can't integrate that. So I'm done. Like there's nothing else that I can do. So I suppose the advice I'm giving is hope that the x's disappear. If they don't, change them into whatever u's they're supposed to be, and then see what results. And don't be disappointed if what results is something you can't do. But once in a while, it'll be something you can. Okay, so I know students sometimes hate when I do this, but can we just stop this problem here? Like there's nothing interesting left to do. Add 1 to the power, divide by the power, yeah, and then change the u's back to x's, right? There's just going to be a big mess with fractions, and there's not a whole lot to be gained by finishing. Rob? Yeah. X, are you still on this one here? Yeah, well, oh, right. How did you substitute x for u when 1 was x minus 1? So the very first thing we did was we let u equal the thing under the radical here. Okay, and so then in the very next step, we just put the square root of u because that was the u substitution that we did. And then separate from that, we had this x squared that we still had to deal with. And so we did this funky technique, but it's really separate. Like what I can say is that it's one substitution where you immediately, like the very, very first step for us after we find a u and take a derivative is to change something into u. We just change it into u. And then we copy what's left. And now this new technique, after we've done that, we've made our initial just change the one thing into a u, is to see, well, if there's still x's left over, maybe we can finagle that first equation. It's really two different things. Good question. Okay, so activity starts on the next page. Plenty of practice with u substitutions. Raise the flag if I can help.